Good morning, ladies and gentlemen. And today we are going to start talking about trigonometric functions and how limits and continuity apply to them. So first thing, let's handle the continuity aspect of it because it's pretty basic. For the most part, sine and cosine themselves are continuous functions. If you think about them, remember what I said, basic definition of continuity is you can draw it without lifting your pencil. So if I was trying to draw that sine curve going on forever, wouldn't be lifting my pencil. So that guy's continuous all the time. Same thing you could say for cosine. However, the other four, tangent, secant, cosecant, and cotangent, are not continuous. There are breaks in the graph. And you could put any one of these into your graphing calculator to kind of see. There's a nice little tangent graph. Remember, it had a vertical asymptote. So that told us it's not continuous right there because I had to lift my pencil in order to draw it. So that's all we really need to say about continuity. Now, because of continuity, there are some special things we can apply in terms of limits. Now, sometimes we have to apply these special things because you can't quite see what the limits are. I'm getting a little bit ambiguous here. Let's just jump into it. Okay, so the first thing is, like I said from the very beginning, you try to plug in first and see what you get. Because sine is continuous, you could just take that pi and just plug it in. So this is like saying, all right, let's see, what is the sine of pi squared over pi plus pi? And all right, so that's sine of pi squared over 2 pi. So that's the same thing as sine of pi over 2. And we want a numerical value for that. And we get ourselves 1. That's our answer. Now we can have infinite values too. So as x is going to positive infinity, we can go ahead and try to plug in. Remember the rules for as end behavior is x is going to positive infinity. We don't really care too much about the 1 and the 3. They're not going to matter as much. So we're looking at this as x is going to positive infinity. So it's like saying pi x squared over x squared, which is going to simplify down to pi. So that is what everything inside the parentheses is going to be. So then because cosine is continuous, we can then just take that pi and plug it in there. And we're going to get -1 as an answer. And those are the easy examples. Now, sometimes plugging in isn't so easy, and we have to apply some theorems, which are some rules that allow us to say things. Now, if I went back to the beginning here, these two theorems, these are ultimate truths. All right, as a matter of fact, pause, copy these down, highlight them in your notes. These are special. Okay, now that we're back, if I try to evaluate this, if I try to plug in that 0, you'd be looking at sine of 0 over 0. And already you can get an idea that's no good because it's 0 over 0. That's one of those indeterminate numbers. And the same thing here. If you try to plug in 0 here, your top becomes 1 minus 1 and your denominator is 0. So again, 0 over 0. Well, we can, and I can explain this all later on. I could tell you with certainty that sine of h over h is going to equal to 1, and 1 minus cosine of h over h is going to equal to 0, as long as h's are going to 0. Now, the reason why I'm using the letter h as opposed to the x's or the thetas or any other kind of symbol that we use is I just want you to understand that this variable is acting as a placeholder. And it doesn't actually matter specifically what it is. It's that these two have to be the same. That's what matters. That has to be the same there. And these guys have to be the same. So if this says a 2x here, this has to say a 2x down there. And if that doesn't say a 2x, the trick, and which is what we're going to practice now, is you have to make it a 2x. I use theta instead. All right, so here's a nice little example. Take a look at this. Now, in order to use the theorem, of course, I should try to plug in first with all limits. The first thing you try to do, you get sine of 0 over 0. That's no good. So we're going to somehow incorporate this theorem here. This one right here, I'm going to circle it. But we first got to make it fit. I don't have these guys to be the same. Now, what I mean is, I wish I had a 2 underneath here. I wish I had a 2 right there. Well, what I learned some another time is if I do something to the denominator, I must also do it to the numerator. So if I'm going to put a 2 there, I have to put a 2 there. That's the key thing here with this. So now, according to that theorem, this part right here, right there, is going to equal 1. So you're going to have this piece is going to equal 1. And you have that 2. And 2 times 1 equals 2. So the trick is with these questions is making what you're taking the limit of to fit the theorem that's most appropriate. Just a disclaimer, most of the time you're just sticking with the sine one. The cosine, the second one, is not used that much. I think there's 1 or 2 examples in the homework. Most of them are sine or some form of getting to the sine. Okay, so here's one. Now we want these guys to be the same. Now here's a case where in the denominator, I've got too much. I've got 8 theta. I only need 4 theta there. Wait a second. Isn't 2 times 4 equal to 8? Sure it is. So let's pull that apart so that we have sine of 4 theta on the bottom. And on the top, we have 2 times the 4 theta. Now, we don't need, in this case, to multiply the top and bottom by anything. We have what we want in order to use the theorem right there. And according to that theorem, that's going to equal 1. And now be careful, because this is technically 1/2, right? This is 1 over 2. So the answer is going to be 1/2. Alrighty. What if you don't have sine or cosine? Well, guess what? You got to make it, like with tangent. Now, we do remember that tangent equals sine over cosine, right? So let's work that out. Sine over cosine over x. And when I do my little same change flip there, we're looking at sine of x over x cosine of x. That's how that simplifies. Alrighty, so the limit as x goes to 0, sine of x over x cosine of x. And look at this. Here's the theorem. That's going to turn into the number 1. What about this cosine of x? Oh, silly goose, you got to plug in. And cosine of 0 equals 1. So you get 1 over 1. That's 1. Here's your answer. Finally, we're going to come up with one that we're going to create our own little rule for. And but I want to work through the example first before we create the rule. So you see we have sine both in top and bottom. So I wish that underneath that the sine 3x, I had a 3x, because then that's the same. And I wish that underneath this sine 5x, I had a 5x, because then I could use that theorem. Well, guess what? We're going to do that. So we're going to take that sine of 3x, and we're going to put a 3x underneath him. But if I'm going to do that, I have to remember to do that to the top of that fraction too. Big fraction bar here. Then we have the same thing for the sine of 5x. And if I throw down a 5x there, I have to remember to put a 5x in the top of his respective fraction. So now using the theorems here, when I evaluate that limit, that's going to turn into 1. That's going to turn into 1. These guys, bam, bam, are going to cancel each other out. The answer to this is 3/5. So what's the trick that I was referring to earlier on? If you have sine of something and sine of something else, you can just kind of know that, see that the answer is going to become that 3/5 right there. Is that always going to work? When you're looking at basic sine like this. If I had stuff that's squared or other things, or it's not going to 0, then it's not going to work out. All right. Talk to you later.